Welcome to Computer Networks. This is Chapter 3, Part 4, Congestion Control. I'm really hoping that this isn't going to be as long as the other sections. This is probably the most abstract, math-intensive part of all of Chapter 3. So I just want to warn you all ahead of time that you may want to have a really good, stiff cup of coffee or some other stiff drink ready to go. But let's jump in to talk about network congestion and how to control it. So network congestion occurs when there's more data trying to be sent than a link can handle. And it's really hard to understand what that really means if you're just used to thinking about like two computers connected by a wire. But remember, IP, the Internet Protocol, is virtual circuits, virtual wires. We don't necessarily know how big the wire effectively is between me and another site. Worse, it could change with every packet that I send. Network congestion leads to a reduced quality of service, and that can be defined as the latency or how long it takes for data to arrive, the throughput. It really just is going to be a slowdown in the overall performance of a network connection. Networks that use retransmissions to compensate for network congestion can lead to congestion storms, where the retransmits have to be retransmitted, and that just adds more data to the already congested network. And then what you wind up with is this whole process of you have more time being spent retransmitting data than you have to actually sending data. And this actually happened back in the 1980s on some of the top tier internet nodes where the effective data rate dropped below 32 kilobytes per second. The rest of it was all retransmissions, and that led to some of the modern congestion control algorithms that we have today. A lot of what we see today is just the byproduct of somebody fixing an oops along the way. So there are really a number of scenarios that help us understand congestion. The first one is that we have two senders communicating with a shared router, but that router and all of the servers have an infinite buffer space. We could also have two senders with a shared router and finite buffer memory between all of them. And that's where we're going to really see the congestion start. And then four senders with routers with finite buffers and multi-hop paths. So some definitions: the sender is the machine that initiates sending data to a receiver. The router is the machine that's kind of in between that we don't normally see, but it's the machine with multiple interfaces. It receives network traffic on that one link, determines the destination, the best route to send it out, and then it forwards the data that it received out over that link. So sometimes this is also called a store and forward device. Because it'll store the received data into its memory and then forward it out over one of the links. In scenario number 3, we're going to see a multi-hop path where we have a router that sends to another router. And so then it becomes really hard to predict what the characteristics are going to be. And then finally, we know buffer. I think by now we know buffer, but it's memory on a host or a router that holds packets that need to be sent or that have been received and moved on to another layer in the network stack. So in the example that has two senders, a router with infinite buffers, we have two senders, host A and B, and they each send data with rates lambda in bytes per second. So lambda in is just referring to how fast is data going into the router. And then we have two receivers, host C and D, that each receive data with lambda out bytes. So how fast is data coming in? So unless you give this a careful read and you pay careful attention to the diagram, it's easy to miss the fact that host A and B are sharing a connection to the router, and host C and D are sharing a connection to the router. And so if this link here can handle R bytes per second as its data rate, we could theoretically have host A dumping R bytes of data into the network, but then host B can't dump anything. Likewise, host C could be receiving data at R bytes, but then host D can't be receiving anything. So really what we want to see is that the aggregate data rates here are equal. or not equal, but they're the equal to R, or less than R. I got to be honest with you. I read through this chapter. I spent the better part of an afternoon trying to parse where the author was going with some of these examples, and I think that they're just too abstract. So what I try to do is think about things from the perspective of some concrete scenarios and how the author's description of them would apply. So in the first case, what I did is I considered a lightly loaded system. So if we go back to this picture, we have the case that host A and B are both sending small amounts of data relative to the size of R. Host C and D are completely ready to receive data. They're not stressing themselves to pull any data off of the wire. So for example, if the link rate is 100 units per second, and the lambda in for hosts A and B total each is 5 units per second. Total data rate is only 10 units per second. At most, one buffer could be used on host A or B, because while A is trying to send, B is already sending, so we got to queue up on A. But then as soon as B is done, A will go. There's really no limit there, or nothing to worry about. Router gets 1 unit at a time. It sends it to C or D. The utilization is total of 10 units per second out of 100 possible, so utilization is only 10%. And our time to send is only 1/10 of a second. Notice it's not 0.5, and that's because our time to send is going to be the total utilization. All right, let's go the other extreme now and think about a maximum loaded system. And this is the point right before overload. So how many units can A and B send before the link is completely filled? Well, if the link can hold R units per second and we split it evenly, then lambda in of each machine can only be R over 2. So at that point, the hosts can each send 50 units per second. We're still looking at only one buffer used on each host. The router still only gets 1 unit at a time. It delivers 1 unit at a time to either C or D. But now the utilization is 100%, and the time to send all of the units becomes that full second. We're using all of it. In the third example, what we have is an overloaded sender to the router. And in this case, A and B each send, or they try to send, as much data as the wire can handle. Now, that doesn't mean that they'll actually be able to send that. In fact, what's going to happen now is hosts A and B's queues, buffers, are going to fill up. So since the link can only handle 1 unit at a time, the router only gets 1 unit at a time. Link R is utilized 100%. Time to send is 200 units. That's 2 seconds. So first of all, that's going to be a problem. A and B will have up to R over 2 packets in their buffer. The high water mark is going to be 50. So in this case, half of the data I'm sending is going to be lingering around in memory, and it's going to keep getting worse if this goes on for another second. So, this is a pretty overloaded situation. The important thing to note is this overload is happening on the senders. The receivers are just like, there's more data. Oh, there's more data. Great, more data. What if... And so as far as the router is concerned, it's just getting data and it's throwing it out there. It's not overloaded. So that's one condition. And then the fourth condition is that we have a mismatched output speed. Suppose that the link in is faster than the link out. Now what's going to happen is the data leaving the senders is going to leave the senders faster than it can leave the router. And so now we're shifting the burden of the queue size, buffer size, onto the router. So do you remember when we talked in the last part about TCP window sizes and the flow control mechanisms? Here's the case where the window sizes would not reflect the congestion. Here, window size will reflect the flow control. Why? Because eventually the A and B hosts are just going to have their window size filled. Like they just don't have any more space for any more packets. Here, in this second case, the router is being overloaded. And so the router is going to have to deal with the flow issues. If we were to look at this graphically, what ends up happening is while lambda in and lambda out are the same, we get this nice linear result of throughput. If we are inside here anywhere, we're less than full utilization. But here we are fully utilizing that link. So what happens after that link? Well, now at that point, the link is completely saturated by both A and B sending and C and D receiving. And so the link becomes saturated, and that's when queuing starts to happen. So if we take a look over here, though, and so if we look at this graph makes it seem as we want both hosts to saturate their links with R over 2. But because of queuing delays, they start to queue up and add up, and we see the shoulder of this return suggests that as the queuing delays start to build, they build up exponentially. And it will never quite get to a delay, and we'll get to almost infinite delay by the time we actually get to this utilization. So what we want to do is pick some maximum delay that we're interested in. And while the link won't be as fully utilized, the delay will be minimized, or at least up to the cap that we've set. And so we might be over here somewhere. And that means instead of R over 2, we might be more like R over a third. Or maybe, yeah, over a third. Some smaller value of R that just manages to keep the delays under control. In scenario number 2, we have 2 senders, but this time we have finite buffers. And once the router's buffers have filled, then we can't put any more data into it. And so then we're going to have to stop the senders. And if we stop the senders, then we're going to have to delay everything. So we also are going to end up having to add retransmissions, because if I have sent a packet to the router and the router is full, I'm going to drop the packet. Or if the router has sent to one of the receivers and the receiver is full, I'm going to drop the packet. And so when we do that, we're going to have to add retransmissions. And if we have a retransmission, eventually we're going to have to resend it. And so the load is going to be higher. To send n number of packets, with some of them being retransmitted, I actually have to figure out what that retransmission rate is, because I'm going to be sending more data. And that just makes the congestion even worse. So the definition that we use for this is something called offered load. An offered load is the rate at which the transport layer sends segments, and that's going to be the original in the retransmitted data. So for instance, let's say that 10% of my data is going to end up being retransmitted. How much do I need to actually send? Well, I'm going to end up sending 1.10 times my size of data. No, I take that back. Whoops. Got the math wrong. Let's say I'm sending 1K packets or segments. So I send out 1K segments, but then 10% of those also need to be sent again. So I have 1K plus 10% times 1K. So on average, that becomes each packet size. So this is, so each packet is one. Sorry, can't do math anymore. So each packet I send turns out to be 10% bigger on average. And so you can kind of start to see how retransmits can really start to degrade your network performance. The author went into a lot of weird detail and not a lot of explanation. So I'm going to try to polish this off myself, and I hope I help and don't make things worse. If I make things worse, just ignore this and follow the textbook. The goal is that you just figure out what's going on, one strategy or the other. We both get to the same place. So if every packet arrives at the destination, then there's no extra load, so lambda out equals the offered load out. And if we saw before, the lambda out was less than or equal to r over 2. And if we know that lambda has to be less than or equal to r over 2, so that retransmits just don't happen, or if the sending hosts know that there are free buffers on the router, then we know that we don't need to do retransmits. So to pull this off, I need to have perfect information about all of my devices. So what this is just trying to come up with is, how do we get, so there's a couple different cases to this scenario. So if there are no retransmits, then I somehow need to know before I send the packet that sending this packet, it will arrive and it won't get lost in a buffer anywhere. And I need to know the intentions of the other senders to make sure that they're not going to send at the same time. I need to know the availability and the capability of the receivers to know that they can pull the data off the router in time. And I need to know that the router doesn't have already a full buffer. And so if I could somehow magically know this, what we wind up with is this weird graph where this is the utilization of, this is basically lambda out across the two different senders. And where they're equal, we get this kind of triangular space where we see the throughput keep increasing until we saturate at 1/2 lambda. After 1/2 lambda, I can't throw any more out there. But you notice before it was at 50%. Now it's not. And that's the effect of retransmits. So the retransmits have kind of pulled that shape forward. They've made, instead of this being angled at 45 degrees like it was before, now it's angled more like 60 degrees because of the retransmits. Case 2, the sender retransmits perfectly. And so here, the sender only generates a retransmission when the packet is definitely lost. So here we assume a reliable network. So we're not saying that there's like any random errors in transmitting the data. The lost packet is only due to buffer capacity. And so in this case, the offered data rate is exactly r over 2. And then this is the quote from the textbook. The rate at which data are delivered to the receiver application is r over 3. Thus, out of 0.5 r units of data, 0.33 r bytes per second are original, and 0.166 r bytes per second are retransmitted data. End quote. And then there's no further explanation of where those numbers come from. So it's not a very clear explanation as to what's going on here. So first of all, let's try to explore why. So if we let x represent the percentage of retransmits, then 1 times 1 minus x plus 2x is having to equal the 0.5r. So where does this formula come from? So this is the number of packets that do not need to be retransmitted. So for instance, if I have 10% of my data needs to be retransmitted, then 90% of it, this would be the 0.9, only generates one segment. However, 10% of it generates 2 segments. So from this formula, we basically can take our retransmission rate and solve for x. And when we do, we get to x is equal to 0.16666r. And then now that we have it equal to 1.66r for the retransmitted rate, because that's what x was really all about, then we can figure out what the data rate needs to be. So I could figure out how they got to the values, and there's the formula, although they never tell you that that's the formula. That took a while for me to kind of figure out, and maybe just because I'm not a math whiz, but that wasn't obvious to me where the numbers came from. The next step is really going to be to look at maybe a little bit more in depth as to why this is what it is. So in this analysis is still pretty superficial. Let's try to do better. So this is not in the book, and I probably wouldn't put this on an exam, but I want to try to build up the math understanding of where this stuff comes from. And this guy, Poisson, which is French for fish, don't get the two confused. It is okay to order Poisson on a menu. You won't get the mathematician. The Poisson probability can be used to find the probability of k events occurring in some unit of time. And there's a bunch of theory that goes behind this, and I do not care that you know that. But what we can do is, if we know what the average likelihood of an event occurring in some unit of time, we can answer the question, what's the probability of observing k of those events? So one of the best examples is, let's say that you have the probability of a failure. You know that in a year, you're likely to see 5 website or 5 computer failures. So now you want to know, what's the probability of 1 failure, or what's the probability of 10 failures occurring in that given year? So if that's the case, we'd say I have e to the negative 5 times 5, say for 10 failures, 10 over 10 factorial. And whatever number that turns out to be, that's the probability of exactly 10 failures in any given year. That's what Poisson probability is used for. Now, if I'm more interested in what's the probability of 0 through 10 failures, then I would use this form. What we're going to do is we're going to take the summation of all of the different k's up to the number. So if I want to know what's the probability of seeing up to 10 failures per year, so 0 failures, 1 failure, 2, 3, 4, all the way up, I would just sum up all of the individual Poisson probabilities. And so we could do it that way, or we could use the MATLAB built-in function, POS-CDF. If you've had stats and probability, hopefully you've seen the term CDF is a cumulative distribution function, and so this is a probability density function. We're going to accumulate those, and so that's just all we're saying. So just take that as truth, and we'll move on. So suppose we send an average of 1,000 messages per second. That's RL. And the receiver can handle that number, at least that number. Any more than that will need to be queued. So we can queue up to 10 packets without losing any. So then we can ask the question, what is the probability that we can observe 10,010 or fewer messages in a given second? Well, we can turn to Poisson, and we can say 10,010 out of 1,000 average will happen about 63.18% of the time. So how did I get that 10? If there's 10 queue slots, then I can only handle at most the number that I can handle plus the 10 that go into buffering, right? So that means, though, that 36% of the time we send more than that, they'll be dropped and need to be retransmitted. So for every message that we send, we generate 1.36 times the network traffic. And so now that we have the formulas, we can actually calculate this. And so 1.36x is equal to 1/2 R. X, our percentage of retransmission messages, is 0.367, and retransmits is, look at that, about 1.33 R messages. It just happened to have worked out that way. If we change things around, we're going to get different numbers. So if your system can handle a different number of messages, for example, if the system can really handle 10,000 messages per second, what is the probability that we're going to see 10,010? It's going to be a lot smaller. What's the probability that we'll see more than that? It's going to be a lot bigger. And so what's the probability we can't handle that? It's going to be a lot smaller. So this is just a really nice tool to be able to get a first blush estimate of how can your network handle the given load. And you'll notice that if you really want to handle this, we got to make sure that we're well below the maximum. And in fact, the Poisson probability gets us to the rule of 10, which means the departure rate should be 10 times the arrival rate to make sure that we never have an overload in the queue, in the buffer. So that would mean that, to be totally honest with you, we would need to have the receivers handling 10,000 messages per second, and the senders only sending 1,000 messages per second, so that we never jump up and have things being queued up, right? And that feels like a lot, but when you start doing the math and you apply this formula, that's what the mathematics actually say. And from experience, if you're going to do like a safety critical system, this is what you're going to end up having to show. Oh boy. Scenario 2, case 3. We're still in scenario 2. Premature retransmits are not detected by routers and switches. They just look like regular data. And so what ends up happening is if I have a timer that times out too early on one side or the other, and I retransmit some data too soon, what it's going to end up happening is the router is going to see that data and it's be like, oh, all right, here's more data. And it's going to pass it on to the next system. And as a direct consequence of that, we're going to add more congestion to the receiver's already congested links. So what does section scenario 2 tell us? It tells us that there are several conclusions that we can make. First, we will never have perfect knowledge of buffer state across multiple links. I can never know what routers are. I might not even know what routers I'm going to be sending my data through. That's completely opaque to me. So there's no way that we can know that information. So my congestion control needs to be agnostic to whatever the buffer state is across all of those links. Number 2, average sending rate needs to be maxed out at whatever the rate is divided by the number of senders. And so that becomes a huge problem. If we're just doing 2 senders, it's 2. What if I have 10 senders? Well, that leaves me with a much smaller fraction of the network. For example, we have a 10 gigabit connection to the internet on campus, but I'm sharing that now with several thousands of users at any given time. I need to make sure that my sending rate is well below that rate, because I'm not going to get the full 10 gigabit. Network congestion leads to retransmissions in order to handle dropped packets, and additional time is needed for timeouts and retransmits, and that's going to slow down my data rate. Retransmissions, though, can add to the congestion workload of an already overloaded router or link. The way that we deal with that in the network world is we'll just have multiple routers with multiple links to different paths to get to the same destination, basically. Unneeded transmissions by sender in face of large and unpredictable delays can cause the router to use its link bandwidth to forward even more unnecessary copies of data, and that can just add to additional congestion and slow everything down. Scenario 3, we have 4 senders with finite buffers and multi-hop paths. I think the big observation that they give here is that you have a sender who is sending data through multiple routers, and as this sender is sending data, it interferes with another sender being able to send the same data. And so what ends up happening is your data rate starts to climb, it's fine, until you hit a certain amount of capacity, and then you start getting this congestion storm, and the data rate quickly drops to almost 0. And so whatever congestion control algorithm we use, we want to make sure that we never get into this space, because that's just not a good place to be. So there are really two approaches to congestion control. The first one is what we call end-to-end congestion control, and there the network layer. So remember, the network layer would be, for us, the Internet Protocol, and that provides no support to the transport layer as far as controlling congestion. So in the end-to-end, it's the TCP layer and only the TCP layer that is responsible for congestion control. The presence of congestion then has to be inferred by the TCP layer because it doesn't have access to buffer space or network utilization or router connection information. There's no availability of that. The second kind of congestion control is network-assisted congestion control. And here, the routers that are between me and the remote side can indicate that they are congested. And what they'll do is, as they store and forward on datagrams or packets, they will modify the content of the packet, the kind of the envelope, kind of like what the post office does when you mail a letter, if you've ever mailed a real letter. Well, your generation hasn't. But they'll take your stamp and they'll put a stamp on it to cancel your stamp. They'll put barcode on it to help on the delivery. They might even put a little label on it if the label isn't, or the address isn't clear. I mean, they'll do all kinds of stuff to the envelope, but they don't touch what's inside. They don't change the letter that you've written. They just change the envelope. Routers can do the same thing. They can change the delivery envelope without actually changing the contents that the application layer expects. And in this case, the router can actually flip bits that say that its link is congested. Some protocols allow that. TCP/IP does not. So as no surprise then, TCP does not use network-assisted congestion control. It does use end-to-end. So how does TCP infer congestion? Well, there are three rules. Sender limits the rate at which it sends traffic as a function of perceived congestion. And so what will happen is we're going to make a guess of how congested things are. And then sender will increase the rate if it determines very little congestion. So if I'm sending data and getting replies back right away, I'm going to start revising my opinion of what the congestion really is. And then sender will decrease the rate if it determines that there is congestion. So if I'm sending data out and I'm not getting replies back, then I'm going to assume that the link is just pooched, and I'm going to have to slow down. So this really resolves to four issues. One, how does the sender limit the rate? Two, how does the sender determine that the link is congested? Three, how do we update our view of what the congestion really is to update our send rate in response to this congestion? And four, what happens if we get it wrong? So in the first case, what we're going to do is, in addition to the data size window that we saw in the TCP header, inside the TCP kernel, we're going to maintain another variable called congestion window. So this is not exchanged between the two TCP endpoints. And what this is going to do is it's going to do a self-imposed constraint on the rate at which TCP sends data out over the network. The rule is that the amount of unacknowledged data at the sender cannot exceed the minimum of either the received window from the TCP header, that's the remote guy's window, or my local understanding of the constraint window. So, the congestion window. So note, we can look at flow control because there is a part of this. This is flow control. This is the other side saying, "Uncle, don't send me any more data. I cry mercy." This is, I think the link is kind of crappy and I need to slow down. So this is congestion control. And it's the minimum of the two that kind of make flow control and congestion control feel a little bit entwined. So for now, if we just assume that the receive window is way bigger than the congestion window, we can just ignore the interaction between the two windows and just focus in on the congestion window. So this satisfies issue number 1. Before initiating a send event, we ensure that the amount of unacknowledged data is less than current window. And if it's not, then we do not admit new data into the socket, into TCP. It stays in the application's memory. It may slow down the application, but that's kind of what we're trying to do here. So how do we adjust the view of what the congestion status really is? Well, what we're going to do is TCP is going to maintain a clock for each packet that it sends. And we're going to measure from the time that I send the data until I get the acknowledgement back. And that time delta is going to be used to update the congestion window. And so from this perspective, TCP is self-clocking. So I'm not dependent on synchronizing my clock and the remote clock. I'm just going to keep track of the clock myself. The remote's going to keep track of its own clock. And hopefully together we'll come up with a view of congestion that makes sense for both of us. And we may end up with different numbers because my path that I use to send to the receiver might be a different network path than the receiver has to me. So the way the internet works, there just may be a different routing path between these two different devices. And there's going to be different congestion between these two different devices. So both sides are going to maintain their own congestion window. The rules then are a lost segment indicates some congestion. So if I send some data and don't get anything back, that tells me that I've sent too much data. So then I should reduce the congestion window. On the other hand, every time that I send data and I get a reply back again, that tells me that the network is working and it can handle more data. So I should slowly start to increase my window size to let more data be sent. Or I could just probe. I could throw a bunch of data out and keep increasing the data rate to probe for data until I find that limit that the network can't handle anymore. So these are the mechanisms that we're going to have to understand what congestion is present. And now all we need to do is take these observations and turn them into a formula to revise the size of the congestion window. And that's the work of Jacobson. So Jacobson's algorithm for congestion control has three parts. Part number 1 is called slow start. And at the start, the congestion window is going to start at one maximum segment size in the time that it thinks it's going to take for that to send. So our current congestion window is going to be determined by the number of bytes in the segment size divided by the round trip time for that byte. So for example, if MSS is 500 and RTT is 200 milliseconds, the resulting rate is going to be 200 kilobits per second, and that's our first guess as to how fast the network is. Now, that's a pretty slow network. But what will happen is every time we send a segment and it's acknowledged, this allows me to determine that the link is not congested. So what I'll do is I will send or increase Cwind by 1 MSS for every segment that gets acknowledged. So the first time I send a packet and I get a segment and I get a result back, that's 1 MSS. But that gets added on to the MSS that I started with. So then the next time I go to send some stuff, I'll send 2 at the same time. And if they both get acknowledged without timing out, I was at 2 MSS, and now I get to add 2 MSS. So now I'm at 4. The next time I'll do the same thing. I'll send 4 out. If I get 4 back, then I'll go to 8 MSS, and I'll keep doubling the congestion control window. So what will eventually happen is we will get to a point where we'll kind of grow and then we'll crash. So let's just draw this out. So we start here, there's 1, 2, 3, 4, 5, 6, 7, 8. So the first time I send, we're at 1, and then we go to 2, and then we go up to 4, and then we go all the way up to 8, and so on. But what's going to happen is if there's a fault, we're going to remember where the fault occurred. And I want to remember where the fault occurred because I want to use that as kind of an upper high water mark of this is where the bad stuff happened. And we're going to call that bad stuff the threshold. Kind of a, not sure why they would call it a threshold. It's, oh, I know, because it's a threshold. So this is the threshold that we're going to go up to in the future. We're not going to go above that for a while. And what we're going to do is we're going to go back to slow start, but we're going to come back to, actually, I guess I drew this at the wrong space. The threshold should really be at about half. And we're going to move our way back up to this threshold. And once we get to that threshold, at that point, we're going to be done with the slow start algorithm. Now, it's possible that the next time I'm trying to climb up to the threshold, let's say that the first time we got all the way up to 16, or 32. Let's say that we got to 32, and then we had an error. The threshold would go to 16. If I have another error, then the threshold is going to go down to 8. And if I climb my way back to 8, then we're good. Then we're done with the slow start. We're going to go into the next step, which is called congestion avoidance. So this slow start kind of helps us suss out where the load can safely be. And if you're familiar with any algorithms, this is very similar to what's called a binary search. So we're going to make these big jumps pretty quick to try to find how good our network is. Then, once we leave the slow start phase, we're going to go to congestion avoidance. And during the avoidance phase, every time that I get an acknowledgement, I'm going to add MSS over the size of cwind onto the cwind estimate. So, for example, if I send 10 segments out, they both filled up 10 MSS, and whatever the size of this was, I'm going to end up adding 1 MSS to the cwind. So you can imagine that as we start just sending huge gobs of data, eventually the congestion control is going to slowly wind its way up, and it's going to keep increasing this kind of slowly but surely, never doubling like it did before, but just slowly going up until we start losing acts again, and then it's going to come back down. So if we were to kind of measure the scope of cwind, it's going to go through the slow start phase, and then it's going to be incremental, and then it's going to be really small changes over time as the linked state changes, which is ideal. It's exactly what we want. We want to try to always be tending toward full utilization of the network link, but backing off so that we're not just spending all of our time retransmitting. And then there's a third state, and that is the fast retransmit. And if you recall back from the third part of this series, if we send 3 duplicate acknowledgements, we'll move into the fast retransmit phase. And at that point, as part of the fast retransmit phase, we're going to drop cwind by half. Because what that means is we've lost a big chunk of data. And then we will then slowly start to increase until we get back to the threshold, and we'll move back into avoidance phase. And so we can actually work our way through the finite state machine for congestion control. And this is a good thing that we can maybe do together during class, and you'll probably see a homework on it. So if I forget to go over it in class, someone asked me to do an example of this in class, because I'm sure that you'll see this on a homework. So you want to see how to do an example before you do the homework. And believe it or not, the last slide after like a 50-hour long lecture on TCP, at the IP layer, if we were to do, so one of the things that's being added or proposed for very modern implementations of TCP IP is this thing called Explicit Congestion Notification, or ECN. And this is trying to go to a network layer-based version of congestion control. And so at the IP layer, there's a couple bits that we can add to both tell the routers that we pay attention to ECN, and the routers can set to tell the TCP layer that it understands ECN. And then the router can pass on a set of bits that says a link is congested. So what will happen in ECN then is, let's say that I have that multi-hop example. If a router like 5 hops away is congested, as it sends me data, it can mark the ECN bits, and then the next router in the phase can say, do I have another path to get to the destination? Because, like, let's just draw a picture. Let's say that I have host A, and it's connected to router 1. And router 1 is connected to router 2 and 3. And router 3 is connected to host B. And router 2 is connected to router 4, which is connected to host B. Okay. So if host B, this link is the fastest link that's been determined, but all of a sudden it gets considered to be congested, router 4 can say, I'm congested. Router 2 is like, I don't have any other path to get to host B, so it's going to report that I'm congested. But then router 1 is going to get that message, and it's going to be saying, well, wait a second. Router 2's got a congested path, but router 3 doesn't. So now what I'm going to do is I'm going to re-vector the data from host A to host B to a non-congested path. On the other hand, if we're going to a host C, and this link is congested, and this link is congested, and there's only one path, then host A is going to be told that the path to host C is congested. And then it can update its understanding of the congestion window based on that. So like I said, this is a newer standard, and so it seems to be a pretty good approach, but not all networking gear supports it. I think the standard came out 2015, so some of the older stuff might not. I haven't had a chance to look at Wireshark to see if any traffic does, but maybe that'll be a nice lab for us to see if we can find an example that uses ECN. So anyway, there's TCP. This lecture went as long or longer than I hoped it would, and there's still more to cover. So, but there it is. I will see you in class or see you in the next video.